All right, hopefully that was a good introduction to the different working parts of OpenQuake GIS and the plugin. I'm going to briefly switch back to the spreadsheet with the questions that we have for you on the side. So I suggest that you download this spreadsheet and start using OpenQuake to fill in these tables, running different calculations based on slightly different assumptions in each case. And tomorrow we'll have a session where we can present some of this work as well.
Can we give out stickers for anyone who's filling it in?
We do have OpenQuake stickers if anybody's interested. So tomorrow, if you do manage to fill in all of these tables, you can come and show us, and you'll get one of these stickers.
They're cool stickers, guys. Matte finish, plastic feel. They work well in a water bottle. Yeah.
So maybe I'll just do one example again for a few of you who asked me to repeat some of the steps, and then we'll move on to the damage and loss estimates for this scenario. So what I'm going to do is, instead of using the NBCC 2015 GMPs, the next set of questions here is, could you also plot the ground motion fields using different GMPs, maybe also for the same tectonic region, and look at the differences in the patterns of ground shaking and the maximum predicted intensities. So let's work with the first of these three GMPs. So we can again go through some of the steps. And I'll also introduce the Monte Carlo simulation of GMPs instead of just using medium fields. So again, to just repeat, what we're doing now is instead of using the NBCC 2015 GMPs, we're switching to different GMPs also designed for stable continental regions in North America. These are not the NGA East 2 GMPs, which will be part of the 2020 Canada model, but slightly older GMPs, also stable continental. So we are using the same rupture, so we don't have to upload the rupture file again. The only thing that we will change in the configuration file is, let's say, we're changing the GMP to using one of these. So let me just change the description of my job file. We have these, some of these suggested GMPs in the handout as well. Feel free to try out other GMPs that you think might be more suitable for this region as well. Oops. We can use the same, I'll upload the rupture. Show you XML file. Rupture mesh spacing, let's keep that at 2. Using the region grid, I lost that information. Let me quickly fill that in. Minus 72, 49, minus 68, 49. We're creating the polygon of the region that we think will be affected by this earthquake. 68, 46, and minus 72. 46. You can go clockwise or counterclockwise. You just have to go around in a consistent direction. Again, let's use uniform site parameters. And here, PGA, say, let's just do PGA for now. So again, let's just do the median. So truncation level 0, everything is the same. Download the zip file. It will again be called scenario hazard.zip. I will just rename it to something more sensible. I'll put it into my working folder for this scenario. So just renamed it to something that I can recognize later on. And then the last step is to run the job through the QGIS interface. So you can click on the play button. You should see the previous calculation that we ran. You can run a new calculation and provide the zip file that we just created. So this is the shallow scenario in Atkinson mean. So it's done. Again, we have a list of outputs. We can load the ground motion fields as a layer. In this case, we only have a single GMP and a single intensity measure and a single ground motion field. If we load that as a layer, you can see the difference between the shaking patterns, just because of the type of distance measure used. Is different between the hypocentral distance and the RGB distance. So you're seeing the differences in the patterns of ground shaking. So you see circles centered around the epicenter here, or around the hypocenter here, and you see ellipses around the rupture plane. Let me rename that as well before we move on. And to save these results are loaded as a temporary file. If you want to save them to disk, you can save them as geopackages or shapefiles or other vector formats. Just provide a path as usual. I'll call it median PGA. Say okay, and then that should be stored on my disk. So the next time I load up the QGIS project, it will still be there. All the temporary layers will be lost. So if you want to save your results, make sure that you save the temporary files. We have, let me just go through the list of questions that we have for you that we'd like you to do. Here is the spreadsheet. We went through how you can find the maximum PGA in the entire study region by looking at the attribute table, or you can download the CSV files and find the maximums from there. We provided you with a VS30 file that covers this small region. So all you have to do if you want to include site conditions in your calculation in this through the VS30 proxy is when you prepare your job file in the site conditions section, instead of using uniform site parameters, you would provide the VS30 file. You would have to upload the VS30 that we provided you in the scenario folder. It's called VS30 _ shallow scenario. You would upload that, and everything else, I guess, still stays the same. You can download the zip file and run the calculation as usual. So that's one thing, including site conditions. Then the other thing that you can do is look at the effect of different GMPs, look at the patterns of shaking, look at the maximum intensity measures. So using different GMPs, we'd like you to fill this table as well. And do this exercise before you leave tomorrow. or if there's time today, you can do that today as well. And as we were discussing before, you can propagate the uncertainty in the GMPs onward to the risk. So to do that, instead of looking only at the median ground shaking, you can simulate multiple ground motion fields for the same scenario. And the important parameters that you would change would be the level of truncation. Here, instead of 0, you can put 2 or 3. So that means you're moving 2 or 3 standard deviations away from the median and sampling from this truncated log normal distribution. And instead of 1 ground motion field, maybe you can run a Monte Carlo simulation of 100 or 1,000 ground motion fields, depending on how powerful your computers are. 1,000 ground motion fields should run pretty smoothly within less than a minute on my old Mac. You can try that. So the only difference here, when you're doing a Monte Carlo simulation, is you increase the level of truncation up from 0 to, let's say, 2 or 3 standard deviations away from the median. And then you can increase the number of ground motion fields from just the median field to 100 Monte Carlo realizations of ground shaking. That will help you fill this table, which is task 2, ground motion fields using Monte Carlo. And we won't have time to do that in today's session, but because we have to move on to damage and loss calculations. So now what we're going to do is keep using the same rupture file.
So because I've been telling to people individually, in order to fill this faster, if you go to your QGIS project, there is an option when you will go to upload the GMFs. So let's say for rock, when you click on load layer, there is a button that says load all realizations. So it will immediately upload the 3 GMFs. So you don't have to go and do one by one. So that is quite easy. Let me do it in.
This one has only 1.
This one has only 1. Okay. Sorry, that is the first calculation. Another thing is, some people have asked, okay, where is my data? Where do I go inside and grab the data? So to recap, you install OpenQuake and the calculations are in your computer. QGIS is just a way that we have considered appropriate to visualize the results. But all the calculations are in your computer. Where are they? You have to go to the program files where OpenQuake is installed, and you will see that an HDF5 format, that is an optimized format for data, will have the job ID, the calculation ID, and that is at the data store of your information. So if I want to explore the GMFs and I want to see the data, you have to come here and download it in CSV and place it where you want to have it. The point is, since we generate so much data, we encourage users only to download the data that they actually need. And sometimes when we want running a scenario, you have to do multiple runs before you actually say, okay, this is what I need. So if you want to download some data and make it like permanent in your local folders, you have to come here and download in CSV. You can also download the HDF5 from here, and you will have absolutely all the data. The HDF5 has a less stable version format, between versions, while the CSV is more stable, so that's why we encourage to have the CSV version.
So now the next part we're moving on into damage calculations for the same scenario. So then we're now bringing in the exposure and the fragility files for Canada into this exercise. So let me just open up the exposure summary that Murray has prepared for us. This is in your exercises directory. There's a spreadsheet called exposure model summary. Just take a look at that. So this has some of the information that Murray presented in his talk in the morning. So it's telling you in the two provinces what are the number of buildings of different building types. So these are general building types. Then the specific building types as they relate to earthquake risk analysis. Descriptions, short descriptions of what those building types are. How many buildings are in each of these categories? What is the total replacement value of these buildings? What is the approximate number of people we expect to be in these buildings during daytime hours, during nighttime hours? Because in commercial buildings and in education buildings like this, they would have a lot of occupants during daytime hours, during weekdays, but probably close to 0 people here in these buildings at night or on weekends. So the number of occupants in the buildings, they change quite a lot depending on what these buildings are used for and time of day and week. So depending on when the earthquake scenario occurs, you could have very different estimates of human casualties. So all of this information is summarized at the province level for you for the two provinces. And then you have total sum of buildings for the two provinces. So it's around $5 trillion of exposure in the two provinces. Let me just give you a quick tour of how the exposure files are organized. So I'm going back to the datasets directory. This is one of the 4 folders that you have in the materials that you downloaded today. Inside the datasets directory, there's a directory with the exposure information. So we have 2 big files, one for Ontario, one for Quebec. If you unzip that, you'll see that each of those is a bunch of CSV files. So these represent each of these files is the exposure for one of the census divisions of Ontario, and similarly there will be 98 files for Quebec. And the reason you split them into so many different files is because if you have a single file for all of Ontario, it'll be hundreds of megabytes of information, and you may not need all of that for what specific calculation that you're running. So by splitting your exposure into separate files and using only what you need, you can speed up your calculations and make sure that you're not doing excess computation from what you actually need. So if I open one of these files, let's open the file for the Toronto Census Division. For the files in the Quebec folder, you might see some problems with the accents in the French names. So in that case, you must be careful to open the files using the UTF-8 encoding for CSV files. If you double click on the files directly, you might see some strange names that you don't recognize, so you have to be a bit careful. For Toronto, all the names are in English, so we shouldn't have those problems. So you see that each, let me increase the size a bit and describe what is happening here. So each of these rows represents one asset in your exposure model. And let's see, there are about 50,000 assets in this file for Toronto. Each asset would be a group of buildings that have similar structural attributes and similar occupancy or use cases. So you can simplify your calculations by, instead of doing calculations building by building, you can group buildings that have similar attributes and do the calculations for all of them at the same time. So an asset refers to a group of buildings. So the first asset, for example, here you'll see that it has actually just one building. But some other assets have many more buildings. For example, the fourth asset it comprises 85 buildings within the same. This is at the dissemination area level. So each asset has a latitude and longitude, which represents where these buildings are. If it's a group of buildings, it represents the most representative location for those group of buildings. A taxonomy string describes, in this case, the occupancy class and the structural type. So it's a commercial type 3 occupancy class. It's an unreinforced masonry, low-rise building. And the last part of the string is PC, which means it's pre-code, which was probably built before seismic design regulations existed in Canada. Then there's the number of buildings. Then the next 3 columns represent the replacement cost estimates for the structural components of the buildings, the non-structural components, and the building contents. The following 3 columns refer to the number of occupants that we expect to be in these buildings during daytime hours, nighttime hours, and transit hours. And then all of the rest of these columns, they are not required for OpenQuake. They're not mandatory. But these are something that Murray has added in to be able to aggregate information at different levels corresponding to the dissemination areas or aggregate dissemination areas, census divisions, census division name, census subdivision. These are statistical area classification, land use type, the general building type, the taxonomy strings, earthquake building type. This is the design level, pre-code, low code, moderate code, and high code. The major occupancy classes: residential, governmental, commercial, industrial, educational, and the name of the province and the name of the region in Canada. So having these extra pieces of information built into your exposure model helps you to aggregate information at different levels and for different structural attributes or occupancy attributes. And then you can quickly summarize your damage and loss estimates for across all of these different categories. So this is what a raw exposure model in OpenQuake looks like. It's a CSV file with many pieces of information. So most of you would probably be using exposure files that have been created for you by somebody like Murray. Or if you have your own building inventories, you can bring them into OpenQuake as well. There's a quick way of doing that, again, through the input preparation toolkit. There's a tab for exposure, which is the first tab. If you click on the exposure tab, this is a way in which you can start building these CSV and the supporting metadata XML files. If you have your own building inventories, you can bring them into the same format through this tab. In this case, we're using the files provided to us by Murray, so we don't have to do this. We can use the pre-prepared exposure files. So just wanted to show you what those files look like. And the same file that we saw just now, which is the exposure model summary. Apart from the summary information and values, there are also brief explanations of what are the different tags that you see in your exposure. So these tags are carried all the way through to the loss estimates. So you'll be working with many of these tags throughout. So if you need to know what they are, there are brief hints in this spreadsheet as well. Similarly, there are fragility and vulnerability files that we've provided you already for today's exercises, but again, like some of you might be structural engineers, you might be interested in creating your own fragility or vulnerability functions for building types in that are specific to Ontario or Quebec. You might be interested in looking at the risk modelers toolkit, which won't be part of this workshop. Here, if you look at the vulnerability directory, there are 5 files. One of them is the structural fragility file. So this is linking ground checking to damage levels. And then there are 4 vulnerability files. So these are linking again ground checking with loss ratio estimates for the structural components, the non-structural components, the building contents, and then also the occupants. So these would estimate fatality rates in this case for different building types. So we won't go into that into detail today. If you're interested, then there are other tools that will help you create these files. Going back to the scenario, what we're doing now is preparing a scenario damage calculation. So again, we're back into the configuration file tab. So now, instead of only hazard, let's do hazard and risk. So risk could refer to either damage estimates or loss estimates. Let's start with damage estimates. So I'm going to say in the description, scenario damage calculation. And then let's use the NBCC 2015 GMP, so I won't say anything extra there. We're using the same rupture. We can keep the same rupture as before, the same rupture mesh spacing as before. And now we come to an interesting part, because now we have an exposure model that we're working with. So we may not be interested in producing the ground shaking in places where there's nobody. So we don't want to waste computing time on uninhabited areas. We know where the people are, we know where the buildings are through Murray's exposure model. So what we can do is compute the ground shaking either exactly at the locations of these buildings, but then because there are 50,000 assets, this could really blow up your computation time if you're running Monte Carlo simulations with more than 1,000 realizations. So what you can do in that case is use the exposure model. So you can create an exposure envelope around the exposure model, and then you can use a grid around this envelope. So we're still, for the hazard sites, we're using a region grid. And let's stick with the region grid spacing of 2. But in this case, instead of providing the region coordinates as a polygon, we can ask OpenQuake to infer the region coordinates from the exposure model. And for the exposure model, what we're going to do is in your scenarios directory under exercises, if you go to the Charlevoix M7 folder, there is a zip directory, which is called exposure Charlevoix scenario.zip. If you're curious, you can open up that zip file and see what it contains. It'll be a list of CSV files representing the census divisions that are surrounding this rupture. So we've removed the parts of the exposure from the 2 provinces that are likely not going to be affected by this rupture. So we're just keeping the exposure limited to the census divisions surrounding the rupture. And then there's this XML metadata file with some extra information about these files. So if you're curious, you can take a look into that. Otherwise, we're just uploading that file onto the input preparation toolkit. So I'll upload the exposure Charlevoix scenario.
Sorry, where was that file?
It's under these exercises. So in the parent directory, if you go into exercises, then scenarios, and in the first scenario, there is an exposure file, there is a VS30 file as well. The taxonomy mapping is a feature where if you can link the building types, the structural types in your exposure with the structural types in your vulnerability file. In this case, there's a one-to-one map between the exposure and the vulnerability. So we have separate functions, fragility and vulnerability functions for each of the structural types Murray has in the exposure model. In case you want to map more than one function to the same structural type or assign different functions, you can do that through a taxonomy mapping file. In this case, we won't use that, so I'll keep that unchecked. In this example, we're looking at only structural damage. So we'll only provide a structural fragility file. We'll keep the others unchecked. So I'll upload the structural fragility file, which is one directory about the Charlevoix M7 folder. There's a folder called vulnerability, which has the fragility file, and then for the next example, we'll use the vulnerability as well. So here we'll upload the fragility _ structural.xml file. So if once it uploads, you should see it appear in the drop-down list. Make sure that it's selected. Consequence models are something that I was describing briefly earlier in the morning, where you can link estimates of damage to various kinds of consequences. In this case, we're not going to do that. But, Murray will talk a bit about this tomorrow. So let's use the site conditions file this time. We didn't do this in the ground motion fields part of the example. So when it asks you to select a method to specify site coordinates, let's select the site conditions file. In this case, it's just a plain VS30 file with longitude, latitude, and VS30 values in this area of interest. So let's take a look at what we are uploading. It will be, let me switch this off for now. Under data, we have this group called VS30. Let me switch on the VS30 full grid, so it looks something like this. So this is something that we got off of the USGS server for VS30, the global VS30 server. But this is a very dense file. It says this just the VS30 values surrounding the Quebec City Windsor corridor would be 100 megabytes. So this is millions of lines of information. We don't need all of that. So what we've done is clip that even further just to the area surrounding the rupture. So we have a clip file, which is included in the scenarios directory for this example. So we can upload the clipped file. There's this CSV file called VS30 _ Charlevoix scenario.csv. You can open up that file in Excel as well and see what's happening inside. It's just a long list of longitude, latitude, and VS30 values. If the GMPs that you're using require parameters other than VS30, then you need to include additional columns in this file. In this case, we don't need them, so we've provided only a VS30 column. And let's use the 3 GMPs that we started working with. MVCC 2015. Navigate to the bottom. So we have the central, high, and low. Let's use all 3 of them. Ground motion correlation none. Level of truncation, I'm going to set it as 3 because now we're doing a proper Monte Carlo simulation. Let's keep the source to site distance as, let me actually decrease this a bit, because once you start going beyond 150 kilometers, the amount of damage you can expect goes down quickly. If not, you can increase it further. If you see that you still see plenty of damage at the edges of your working area, you can increase this and rerun this scenario. Let's do 100 ground motion realizations. And then once you have run 100 or 500 or 1,000 of these simulations, you can extract statistics of damage and loss from these various runs. So you can look at the mean damage, you can look at the quantiles and so on. So I'm going to download the zip file again, as usual. It will go into my downloads directory. And again, I'll copy it into my scenarios working folder and rename it into something that is more sensible.
For truncation, why do you pick 3? Do you have a reason?
It's what, no, it depends on what you're trying to model. So if you're working on PSHA for nuclear sites, maybe you're going up to 4 or 5 levels of truncation because you want to capture also the extreme values of
Run
truncation.
it at 5
Okay.
but there's very little between 3 to 4.
Yeah. And sometimes you see like peak values of 3G or 5G, which may not really be reasonable. So then it depends on the calculation and on the GMPs as well. So I've just renamed it to shallower damage. I'll switch off the VS30 for now. And let's run the calculation and see if we run into any errors or if it runs. Okay, you can see what it is doing. If you run into some errors, if you have some mistakes in one of your job files, if you miss a parameter, your OpenQuake engine will try a lot to tell you exactly what it thinks the problem might be, so you can go back and fix it. Sometimes the error messages may not be very helpful, in which case you might spend a bit more time figuring out what went wrong. Well, this is part of the process of modeling and using the software. There's a user forum that we have, which I will show you a bit later. If you want to start running OpenQuake calculations, if you have questions, you can post them on the forum. So now we're seeing some interesting messages here. So it's saying that there's a warning that the closest VS30 value for one of these sites came from more than 2 kilometers away for a particular site. What that means is OpenQuake is trying to associate values from the VS30 grid using the closest available value for each of the hazard sites you have in your calculation. And if the values are coming from a large distance, then it's telling you to take a closer look at what is happening. So most of these values are probably close to the edges of our study area. Maybe there's not a very good overlap between the VS30 file and the study area that we create. Maybe some of the points on the edge may not have VS30 value very close. Like maybe we have hazard sites here, and the nearest VS30 is from 3 kilometers away. So that's probably what's happening here. Anyway, that's not crashing the calculation. It's just showing you some friendly warnings. Meanwhile, the calculation finished, but just let's look at the calculation log as well, because that has a lot of useful information. So it says that we have, even in the split area, we have 173,000 VS30 points because it's a dense grid. And then in our calculation, which we have a region which envelopes the exposed assets in that region. So we have 26,000 hazard sites. So these are being associated, the real study values are being associated with each of these 26,000 sites. Then we have around 50,000 assets in this region, lying on 5,000 sites. So a single site may have more than one asset because you might have different building types represented as different assets within the same dissemination block or dissemination area. And then the next line is interesting because it says 67,000 assets were discarded because they're too far away from the rupture. So they're more than 150 kilometers away. So for now, we're not calculating any hazard or damage for those assets. So if you increase the maximum distance, many more of these will come into our calculation as well. So it took around a minute and a half, and the outputs we have here are, we still have the ground motion fields. So that's the hazard part of the calculation. That's one of the outputs. So you can load that as a layer as before and visualize it. In this case, you'll have not the median, but you'll have 100 simulations of the shaking intensity. So each one of them will look different. The events, in this case, it's just a single earthquake event, but since we're doing a Monte Carlo simulation, the same event is generated multiple times. So if you load that as a table, you'll see a list of the event IDs. We won't do that for now. The interesting outputs for us are the damage output. So there's the average asset damages output and the aggregate event damages output. Let's start with the average asset damages output. Since we're doing a Monte Carlo simulation of the damage for this event, we've run 100 different simulations of the same event. And so the average asset damages would be looking at the average across these 100 simulations of the average, let's say, number of buildings in each damage state. So let's load that as a layer. In this case, the three realizations, they represent the same three GMPs, the central, high, and low. It's just the names are not appearing here. They're showing up as realization 0, 1, and 2. This one is the central. If you're not sure, you can look at the realizations output, load that as a table, and you see the realization ID and the name of the GMP. So if you're interested in specific building types, if you want to look at damage only for low-rise wood construction for residential, you can drill down into specifics. Let's for now look at all building types. We have losses only for structural components, and we have the 5 damage states: no damage, slight damage, moderate damage, extensive damage, and complete damage. So let's look at estimates for the complete damage state. Then there are 2 ways in which you can visualize this on a map. So one thing you could do is just download the raw CSV file of the output, and then you have the estimates for each asset, the number of buildings expected to be in these 5 damage states. If you want to visualize these on a map, you want to aggregate them onto some kind of dissemination area level or census division level. So you can do the aggregation by zone. And in the zonal layer, let's pick census tracts because that's not so fine, so that might be fast. In fact, let me use census subdivisions for now. In fact, I'm going to start with the broadest one, which is census divisions. So you'll see the damage aggregated at the census division level, and discard zones with no points. Questions so far? Any questions from the virtual participants? Let me switch off the VS study. So the census divisions are pretty broad, and they can have weird shapes because they really depend on the number of people within each of these divisions. So around the densely populated areas like Quebec City, a census division might be very small, but then as you go into the sparsely populated regions, a single census division might be really large. So here, like you're seeing in a visual manner, the number of buildings that are expected to be in complete damage state. So this is either buildings that are collapsed or are as good as collapsed. You have to demolish them and rebuild them. So the layer is again loaded on top as usual, and you may want to bring it back into the scenario that we're working on and rename it to something that you can recognize later. Let's rename it to complete damage. And census division. Let me just call it city. Again, you can save the temporary layer as onto your disk. If you click on the small triangle next to it, you'll see the what the different colors represent. In this case, each of these ranges represents the expected number of buildings within those polygons that are in the complete damage state. So the deep red, you have hundreds of buildings that are expected to be in the complete damage state. The light pinks, there's almost no buildings in complete damage state. So you can see that our choice of 150 kilometers around the epicenter was a reasonable estimate, because once we go away from this region, the extent of damage reduces. If you want to now go into the census subdivision level, because now you have huge areas, and you might be interested in looking at where exactly within this huge census division the damage is likely to occur. You can do the aggregation at the lower levels. You can do it at the census subdivision if you're interested. I'm sorry, the lower layer. Again, we're looking at the central GMP, and again, you can look at this, the lower and higher variance separately. OpenQuake doesn't do a weighted mean for you across the GMPs. You're looking at complete damage, and this time I'll choose the census subdivisions. Aggregate by zone. So you can see at the bottom there's a small bar that shows you the status of the aggregation that is happening in the census subdivision level. Since there are far more census subdivisions than divisions, it's aggregating the results from all of the assets within each of these divisions to give you a map at this subdivision level. So now you see that the huge census division that we had here, you see that most of the damage is just close to the river. But even then, most of them do not have many buildings in complete damage. So essentially, most of the heavy damage is concentrated right next to the rupture itself on both sides of the river. Let's bring that also in within. Let me rename that complete damage. CSD, and this is the central GMP. So as you might guess, like if you look at the results from the high variant of the GMP, you should expect to see higher estimates of damage compared to the central. So the three GMPs will give you the range of damage estimates within each subdivision. So again, close to the rupture, the deep reds, you're seeing dozens or hundreds of buildings that would be completely damaged during this earthquake. If this earthquake were to happen again, because this is 350-year-old earthquake. So that is visualizing damage results on a map. Other ways you can interrogate these damage outputs would be to look at the table format. So again, looking at average asset damages, instead of load layer, if you click on aggregate results, it opens up a side window, which is useful for displaying like non-geospatial information. So this is showing now you have the choice of selecting 3 GMPs, looking at the damage distribution for structural damage. If you have fertility functions for non-structural components, you'll have options to look at those as well. And here we're just looking at the summary of the damaged buildings in the entire exposed area. So this is the total number of buildings expected to have some like minor damage, slight damage. It's around 10,000 assets, not necessarily buildings, so this could be more than 10,000 buildings. Complete damage, we're looking at fewer. It's fewer than. You can export the data, so if you can look at the actual numbers. So this is around 300 buildings that will be completely damaged by this building, many more in extensive damage. Close to 2,000 buildings with moderate damage. So this is with the central GMP. Again, if you look at the other GMPs, the number should go up slightly. So many more buildings is expected to be in complete damage based on the high variant of the GMP. And if you switch to the lower variant, you should see far fewer. Yeah, almost 0 buildings, not 0, but maybe fewer than 100 buildings in complete damage state. So you see that there's a huge spread in the estimates just based on the 3 GMPs that we have. We haven't even brought in the uncertainty in the fragility or the vulnerability. So estimates can have a significant range. It's always useful to see such kinds of things when you're running scenario calculations. So now, if you want to drill down into specifics, this is where what I was describing before. The reason why Murray has all of these tags in the exposure model is to be able to aggregate these results at for different types of building construction. For example, the general building tag is I'm trying to check that. Okay, so now I've clicked on the building gen tag. So a new drop-down box should appear where you can now select specific parts of your exposure. So if you only want to look at the wood buildings, it should show you the bar chart for wood buildings. If you want to look at unreinforced masonry, so you can quickly look at the damage estimates for different building types. There's another option here which says exclude no damage, because now we're looking at only buildings which have at least slight damage. If you uncheck that box, you will see that the majority of the buildings in our exposure have no damage at all from this earthquake. So in comparison, the slight damage was 2,000 buildings. So this will typically be the case for many scenarios where only a small portion of your exposure might be affected by the earthquake. So you might want to exclude the buildings that have no damage or loss. So now we're rescaling the chart to exclude no damage. So yeah, you can explore these results at different levels of aggregation. You can select other tags that might be interesting. You can look at earthquake design level. So now you're aggregating buildings only based on how well they've been designed for earthquake resistance. So are they pre-code, low code, moderate code, or high code? And you can see in this case, most of the buildings are low code and pre-code. So you can see how the estimates vary across these. You can explore many other things that I will leave it up to you.
That is good that also you can have multiple tags, but if you would like to see from those buildings that are low code, which ones are reinforced concrete. So you can keep adding tags and questions to your model and get the statistics for the information that is specific.
So how can you get the statistics only from one subdivision?
Only for one census subdivision. There's a census subdivision ID. So if you filter by that, you can select just the one that you want.
For the tags in the exposure Excel file, you have the meaning of the tag. So you can go and if you say, I would like to see it only for Toronto, go and select the one that is for Toronto, and you will have the drop down, and the result will be on over.
Another quick way is to use the information button on QGIS. There's this small eye with a cursor. If you click on that, make sure that on the left menu you've selected the layer that you're interested in looking at. So let's say I'm curious about how many buildings actually are in complete damage in this census subdivision. So I can click on that after having selected the eye button, and it will show me all the information about the exposure, but also there's at the end the OpenQuake result that has been added onto this exposure. So it's this structural components complete damage mean across the 100 realizations, and this is for the central GMP. So it's 250 buildings, 250 assets in this census subdivision. So that could be another way in which you can look at the results. Now I need to figure out how to close this. I'm sure there's a small close button somewhere that is hidden from my view. Yeah. Questions or before we move on?
Do we have exposure and vulnerability information for other cities, for example, for Vancouver? And if yes, where provides that?
Again, like Mario was mentioning before, so there are already these files for all of Canada, covering all of Canada. So I think the maybe taken see what the release process and.
I would actually maybe.
What is it?
Would it be possible for people to get access to the Canadian exposure model?
Yeah, so we have
How are we doing on time?
You got 10 minutes left.
Okay, so let's close on this. So then, you can do similar calculations for estimating economic losses and human casualties. instead of using the fragility functions, you would use the vulnerability functions. So here you would come and say hazard and risk for this one is damage, let's say losses. Let's say loss estimation. And the only difference is keeping everything the same. Instead of the fragility file, you would provide a structural vulnerability file. And you can provide other files. In the data sets, we've provided you with vulnerability files for structural components, non-structural contents, and occupants. You can add in those and run through a similar calculation of losses, economic losses, or human casualty estimates. So I would let me just come back to the spreadsheet here. So we'd like you to estimate some things for damage and losses for the three scenarios. So yeah, so for the shallow water scenario, we ran through many of these tasks, but it would be nice if you can do the same thing for the other two scenarios that we provided you with, and let us know if you have questions or comments. There's also a bigger set of pre-prepared rupture geometries that Murray has provided for Western Canada as well, if any of you are interested in looking at those scenarios or modeling those events. Feel free to do that and let us know how that goes. Yeah, I think that brings us to the end of today's session on scenarios. Hopefully that was give you a good introduction of the tools. The idea is tomorrow we'll switch gears a bit. Maybe we'll do a bit of a recap and move into probabilistic.
Yeah, so thanks everybody for